All right. Hello, everyone. I am making you this special recording to go over the setup and hold time constraint that we discussed through the last two classes. And I got some questions about the details for them, but even it went beyond and asking for the need, the actual need to have a setup and hold time to start with in our circuit and how to find them. So hopefully that will clarify the matter for you. And let's go. Okay, so in our lectures, we described the setup and hold time intuitively, given that we had the D flip-flop itself abstracted as a box. So the representation was just a block that had an input as D, and we have a clock that we know at the rising edge. It's going to sample the value, will sample the value of D into Q. So, but at that abstraction, it does not provide us a lot of details. So we had kind of to use our imagination to kind of imagine and kind of discuss it. In order to better understand the setup and hold time, we will need to go some levels down of our abstraction. So it cannot be a box. Let's go a little bit down. And as you know, we have multiple levels going from the transistor or all the way down to the transistor level itself. So I'm gonna, but before that, let's remember this from our early classes about the sequential circuits. When we talked about the D latch, so the D latch was helping, like the D inverted value is helping to prevent the undesired behavior when we could have, or the risk that we could have R and S, both of them, as one at the same time. This is set, this is reset. So we cannot have both of them at one at the same time. So we kind of added D, and also we added the clock to act as a gate. So whenever the clock is 0, then it doesn't matter what the D value is, because it's going to work. The circuit is going to be like in memory state, and memory state or latching state. Whatever last value is in, it's going to continue to be in there. So Q is going to be, will continue to be Q previous. Now, however, if the clock is 1, then depending on the value of D, or the value of D is going to be sampled by propagating. Please remember this word, propagating or traversing or traveling through the wires and the circuit and the components, going from here all the way will be sampled to Q. So if I have 0, then Q is going to be 0. If I have 1, Q is going to be 1. Now this is the abstraction layer level of the latch, but this is kind of providing you some details. In order for us to understand one more time the setup and hold time, we will need to kind of propose a little bit more lower level of abstraction. So I'm going to propose to you another diagram to represent, that still represents the D latch. If you remember, the latch is nothing but two inverted, in the simplest form with no inputs. It's composed of two inverted or two inverters connected to each other. So that's still the same. So I have the two inverters. Maybe the wiring is confusing you, but if you look at it, it was the same. One of them was feeding into the other. So, but it was feeding, like both of them were looking left. So that's why like we had this kind of crossed wires. But in here, it's the same if you look at it carefully. But if we look at this circuit as a whole, you will find that I have, again, the two inverters. Then I have the clock acting. That symbol means a gate. It's acting as a gate. And that's the purpose of it. If you remember, we said if it's 0, then this is becoming in a memory or a latching state. And if it's 1, it samples D. That's exactly what the clock is doing. And with that bubble, it tells you how that gate is going to be open or closed. So if I don't have a bubble, that gate is open. And open here means it's not an open circuit. Open means it will allow the signal to pass. A gate, like a door. So like a gate. So this one is connected. So open here means connected, and closed means shut. So if I have my clock, if you look at this and I have my clock as 0, that means this is open. The gate, the gate is closed, means shut. So no signal from D can pass in here. And because it's 0 and with a bubble, that means 1. So that gate is open. That means it's connected. So what's going to happen, whatever the last value of D was on that wire, now it's trapped or it's locked. So it's going into this memory state or latching state, and that same value, that last value of D, now is sampled at Q. If the clock is 1, now, and with that, so 1 with the bubble, that means this is now shut, or that that gate is closed, so it's shut, and that gate is open or connected, which will allow D to travel, one more time using the word travel or propagate or traverse. So the signal is going to travel through all these parts until it kind of reaches Q. All right, so it propagates to the output Q. So if I have, for example, 0 in here, 0 is going to be inverted to 1, and then it travels, gets inverted again to 0. So 0 converted inverted to 1, the 1 is inverted to 0, so Q is 0. If D is 1, 1 is going to be inverted to 0, and then travels in here and going to be inverted back to 1, and so Q is 1. 1, 1, 0, 0. So it works, okay? Now, based on this, if I would like then to use it to describe or represent the D flip-flop, if I use the same, then it's going to look like this. And just quickly, this is going to be our master D latch, and this is going to be our slave D latch. So these are the two inverters for the master D latch, and these are the two inverters for the slave D latch. And then I have, this is my D signal, this is my Q, and then I have my clock, but the clock is inverted. So 1 is going to be, the positive is coming in here, and the negative is coming into this one. Just as a reminder, why do we have this? Because why do we have this to start with? Why do we have two latches, two D latches connected? Because if you remember when we said the clock, when the clock is high, during that high, D might change. As a result, Q is going to change. So what we said, we do not want to have that. I just want to have at the time of the clock, at the time when once the clock arrives, I need to have the value of D copied into Q, and that's it, and do not change. So to do so, we said we are going to now split between the two. One is taking a copy of D and then taking that copy and sample it into Q. So if you get the clock, so without the clock, so in here, when the clock is 0, this is going to be 1, so that gate is open. It's allowing D to pass. So it's passing. But the clock in here, because it's 0, that door is shut. So that gate is closed. So only D gonna come in here. Yeah, it might fluctuate, it might go up and down, it doesn't matter. It's not impacting Q. And Q, because this is closed and this is open, it's in kind of this latching state. It's just in memory. It's just the same signal is circulating in here. Now, when it happens that the clock is 1, this is going to be closed because 1 is going to be 0. So this door is closed. This door is open, and this door is open. So that's it. The last value of D that was captured in here is going to go into memory state, and it's also going to pass through that gate to go to Q. We're going to see that in details, but I will just explain it at high level. Now, also I'm adding these points. So these are just like tags. So when I'm talking about any path, for example, or a certain traverse way, it's going to be easier to say I'm going S1, S2, and S3, for example, and so on. So I'm just identifying these points using that code. Okay. Now, let's study it a little bit more. What I mentioned before, let's study a little bit more when the clock is 0. So here's my circuit, my representation. So what I expect is the following. So now we said that the clock is 0. Let's see if that path is correct. So my clock is 0. That means, first of all, this gate in here is closed. So the two are separate from each other. Okay, so Q is deaf from whatever happening in here. Okay, so that's one. So this part, we do not need to worry about right now. But let's see what's going to happen here. So when the clock is 0, this is 1. So 1 is going to open that gate, but it's going to keep that gate closed. So what happens to D? D now is traveling, one more time, is propagating through these gates, through these digital components, passing through or traveling, and then it will come here and stop, cannot go anymore. So this is for the master D latch. For the slave D latch, because this is closed and this is open, as we mentioned, whatever last value is in here, it's in memory state, so it's in latching mode, and that same value that it's circulating is going to be propagated also or be copied to Q. All right, this is how it works when the signal, when the clock is 0. Now let's study it when the clock goes from 0 to 1. So here's my circuit again. So what I'm saying is that my clock is going from 0 to 1. So I would imagine 1 is going to be here 0. So that door is going to be closed. So that gate is going to be shut. So a gate is closed. And then since this is 1 becomes 0 and then get inverted again. So this one is open. So that gate is connected. Similarly, that clock, which is 1, is going to cause this gate to be open, connected, and this one to be closed. Closed means shut, okay? So when that happens, the last value that got locked, let's put it this way, is going to be latched. So the last value of D that managed to cross that gate before it closes is going to be latched in here. So now this is in a memory mode, going to continue whatever that value is. And also that value, because that gate is now open, it's going to travel. So it's going to be propagated all the way to Q. And also it's going to travel in here, but will until that point, it's going to stop at S7. Cannot continue anymore because this gate is closed, right? Okay. So now let's talk about the setup time and the need for it. The setup time, by definition, is the minimum, as we mentioned, is the minimum time the input signal must be stable to be correctly latched at the clock rising edge. Let's see this. Let's see it. What we're saying is, here's my clock, right? If we go back to our abstraction, just for a second, imagine the abstraction. So this whole thing was just a block, right? It was just a block. I had a clock, I had D, and I had Q. Theoretically, I expect if D, at the rising edge of D, I expect the value of, at the rising edge of the clock, I expect the value of D to be copied in Q. So at, let's say at time T0, at time T0, let's call it T0. So at T0, I need the value, which is the time the clock happened. I need the value of T0 to be copied to Q. But unfortunately, that's not the case. When you look at that circuit, you will find that the clock in here, yes, it comes fast and it opens that gate and it will go close that gate and close this one and open this one. We understand. However, that D at T0 will need some time, actually to travel, right? So to travel here, then here, then here, until it comes in there. It takes some time. It's not very quick. It's not like quick. So if I say, hey, I'm gonna now switch, I'm gonna close this, whatever value, whatever last value of D, I needed to copy it in there. I'll say, hold on, what you have in here waiting at the gate happened sometime in the past, not now. It's whatever you have at the gate is the signal that D had to travel sometimes in the past. Let's say give it 1. It uses 1, whatever 1 is. It's a time unit. Let's just call it 1. So D needed 1, 2, and 3. Now I'm oversimplifying it because again I'm using an abstraction. Reality is a little bit different. If we now need the exact, we need to go at the transistor level. But for now, let's just discuss it at that level. So just think about it. The clock is quick. It opened that gate and it's closing this one. So whatever value was in here of D is gonna now be latched and propagated. But I'll say, hold on, what you're sampling is not the one that you're looking for. It's not the one that happened at the time of the clock. It happened earlier. So because I still need time to travel all that path and until I'm able to kind of properly sample or get latched. So that's why the idea is that we are saying that then the setup time, it's the time needed for the signal D to travel through the path D to S1, S2, and S3. So if we go with the example with the 3 time unit, just for the sake of the discussion, so I would say that I need D to be ready at T minus 3. It needs to be ready from that time. So here's the clock. So when the clock's still going to happen in the future, I'm ready because that signal at T minus 3, T minus 2, T minus 1, T0, at the time the clock happens, so you're properly sampling the value the value of D that you were looking for. Otherwise, you're risking sampling something else. If D comes late, if the value you're looking for is coming late, before it I had noise and all of that, as we mentioned, for the propagation delay and all the delays, time clock to Q, propagation and all of that. So your signal is coming late, coming T minus 1, then you are risking that the gate is shut and this one is open. This one is shut and without properly sampling the value that you were looking for. So that's why we said you need to be stable at the setup time, which has this calculation. It goes a little bit more, but you get the idea. We need that setup time, which is the time for the signal to be ready when the clock comes and open the gate. I'm properly sampling the right value that I was looking for. So this is kind of that green path that once the gate opens, then I have the right value from T minus 3 that needs to go in there. So that's why we need the setup time. So I'm just giving it this animation that what's the risk if I miss it? It could be this. So you could be letting other values pass and I might have missed it altogether. I just came late and the door is closed and the other door opened for other values, not me. So that's kind of, hopefully that will just give you some visualization of what I'm talking about. It's not exactly one-to-one, but you get the idea. Okay. Now going to the hold time. So the hold time is the minimum, by definition, is the minimum time the input signal must be stable after the clock rising edge. So now, again, ideally speaking, and if we abstract this, we know that if the clock, when the clock kind of is going or flipping, when the clock is changing, I'm expecting the value, whatever latched value, now to go to be sampled at Q. Now, problem with that is the following. Theoretically, or ideally speaking, the clock is opening this gate at the same exact time it's closing this one. Unfortunately, that's not the case. Because of the inverter in here, because in the inverter, yes, it's opening the gate, but this one is like, imagine it like a rusty old valve you're trying to close, while this is an electronic gate. So this is very quick, but this is taking some time. So here is the risk. You had the stable, and yes, you had the desired value correctly, is coming in, all of that's fine, but still the gate did not fully close, which could risk that you have an undesired value came through some contamination delay, that random signal quickly passes through the gate, and since this is open, so that value is gonna loop and then come into that memory state and then go and change the value of Q. So this is the risk that we're looking for, which is that part. So that's why we said D needs to be stable for some time until this is completely closed. So the difference between the clock, one open and one closed, is what is causing that risk. So that's why we need to have the signal stable for a little bit longer until we are sure this is now fully closed, and then you can change the as you want. So the risk of the D value can be altered before the gate is fully closed. Can you think of an animation for that? I kind of came up with one. So you're safely into the elevator on time, everything is fine, and then you have this undesired person jumping in, running quickly and jumping in before the door completely closed, and might change things, might alter the final results. So anyway, I hope this made the topic clear for you. Now you better understand why we need the setup, why we need the hold time. I would recommend please go back and review the last two classes one more time and repeat again the examples and do the calculation, and hopefully it's going to be much clearer for you. All right, thank you.